Hi everybody, it's Mr. Pope from Wilmington Grammar School for Boys, and in the ninth session of mechanics, we're be looking at centres of masses using calculus. Okay, so previously we looked at wireframe models and laminas, mainly rectilinear laminas or laminas that involved really simple circular shapes. Suppose now we're going to be looking at solid wireframe or just solid models and laminas. So let's just look at in general. Now, suppose I've got my function of x looking like this. So this is my function y equals f of x. And let's suppose I'm interested in the lamina that's dictated between the lines x equals b and x equals a, and is bound by the curve y equals f of x and the x-axis like so. So we're talking about this lamina here. Okay, so you've got a solid sheet lamina, so it's infinitely thin in, if you'd like, the dimension that's going into the iPad. So it's like a sheet. It's like if I printed out these notes and I cut this out as a piece of paper, it would just be a sheet of paper kind of thing. So what we're going to do is we're going to imagine that I'm going to divide f of x up into these infinitesimally thin width rectangles, and I'm going to play around with the centres of masses of a particular rectangle. So, okay, well, the centre of mass of this rectangle would be dead in the middle. I'm hoping you'd get that just by symmetry. Okay, so what I'm going to do is I'm going to let the centre of mass of the lamina have coordinates of x bar, y bar. Okay, x bar and y bar being the mean. So first of all, if I want to consider the following, I'll remind you from either year 10 or year 9 or whatever you've learnt it at school, is the whole mass equals density by volume, or in this case it will be area. So mass is proportional to area, and the constant that we're timesing it by is essentially the area. Technically this should be a volume, but if we treat this as an infinitely thin lamina, then essentially it's proportional to area. So what we say is the mass is some rho, which is the density, times by, and we now know how to deal with the areas using calculus. It's the integral between a and b of fx with respect to x. This is really important. Now, for the purposes of the questions we're going to be doing here, we're going to be dealing with uniform laminas and solids. So treat laminas as like sheets and solids as in physical objects like a block or a cuboid. And essentially, if they're uniform, it means they have the same density throughout the structure. So you'll actually find, okay, that for the centres of masses we're dealing with in this chapter, the rows are going to cancel, or rather everything is going to be rho times something, and you can just treat it as a constant. There's a constant density, so you can take it out. So the mass of the object is essentially rho times by the integral, the area of the shape. And if you wanted a three-dimensional area through volume revolution or a double integral or something like that, then of course you just have rho times by the volume, whatever it is. But in this particular case, the area, when defined in this way, is just that integral. Okay, now let's go about working what x bar and y bar are. So let's have a look at x bar. Well, if we remember what we were talking about last time, x bar is just going to be the sum from I is 1 up to n of every x coordinate of the centre of mass times by that particular mass of an object. Okay, why is that? Well, you know, if I had a square like this and a semicircular thing like this, and let's say the semicircle was there and the square was here, and you had a centre of mass of the square here and a centre of mass of the semicircle there, then what would you do? Well, you define a coordinate axis. Let's say the bottom left, we'll call that xy, and then if you wanted the x coordinate, you know, you take the x coordinate of this thing and times it by the mass of the square. So you'd have the square x coordinate times by the mass of the square, and then you'd add the semicircle x coordinate times by the mass of the semicircle, and then you divide that by the total mass, wouldn't you? So, you know, just a reminder of what's going on. You're taking a weighted average. So the x bar is going to be the sum of xi times mi, and this is going to be over the sum of all the masses. But really, this thing down here, the sum of all the masses, we know what that is. That's just rho times by the integral. So that's one thing done. What about the top thing though? Well, let's have a look at what's going on here. The x coordinate, what happens to the x coordinate as dx? As dx tends to 0, so this width here gets smaller and smaller and smaller, then essentially the xi stays the same. Now technically, you know, when this squidges together, you've got a rectangle looking like this. It's infinitely skinny, and the centre is there, and you treat whatever this is, your xi, like that. Essentially your centre of mass is the interval itself. So really the xi stays the same. Now what about the mass? Well, the mass, what's that going to be? Well, that's just going to be your integral of fx dx between xi and xi plus some delta x, some change in x, in this case it's dx. And then this needs to be summed up of all those infinite strips. And then this all needs to be, and then, well, think about it, the mass is technically rho times fx times dx. And I'm running out of space here, this is looking a bit clumsy. Let's write this out again. Okay. Let's do this step by step again. So there's still a sum from I up to n this case, but now dx is tending to 0. That means n is tending to infinity. There's an infinite amount of strips. So that sum is going to become an infinite sum now. And if, as I said before, xi is just going to stay the same, okay, because it's just the x coordinate in general, and that's because as the width gets thinner, the middle of the rectangle is just where the rectangle is in the limit when dx tends to 0. The mass of the object is the integral between xi and xi plus some delta x times by rho times f of x dx. Whenever I'm integrating a rho times fx dx, I'm looking at the mass. So all I'm doing here is just mass position of the centre of mass. And then on the bottom, notice we've still got the sum of all the masses, so this is going to be the integral between A and B of rho fx dx. And because rho is a constant, I can take that rho on the outside like so. Okay, now look what happens to the top. Well, what can we do? Well, I don't need this xi anymore, since, you know, it's just the x coordinate at that point. And since I'm doing the infinite intervals between 1 and infinity for the xi's, and it's going up to n, where n is infinity, then really that's just covering the entire interval from a to b. So this whole thing can be tidied up as the integral from a to b of rho times by x times by f of x dx. And this is over rho times the integral of a to b f of x dx. And because rho is a constant, I can take this rho out like so. And then you'll spot that in general this is x bar, but for our specific constant density, x bar is just going to be the integral between a and b of x times fx dx, and this is going to be over the integral of a to b of just fx dx. And in general, this is what we're going to be working with today. Okay, you're not going to be told these formulas, you're going to have to figure these things out for yourself. Now, notice there's a similar argument here. Essentially, it's the sum of the moments. It's always the centre of mass, or the distance of the moment, times by its mass. So this is kind of the distance of where the mass is acting, and this is the mass itself. We're looking at a moment here. Now, we can pull a similar trick with the y-coordinate, and that's quite easily done as well, because it's going to be the same deal. It's going to be over the mass, which is the integral between a and b of f of x dx, and it's going to be the integral at the top between a and b. It's going to be multiplied by fx dx, but of course there's rho's on the outside bit. But think what actually is going to happen now. What is the y-coordinate? It's not just simply where the x-coordinate is now. The y-coordinate clearly here is just y over 2. And since y is f of x, this just becomes a half times by rho, and this just gets multiplied by another fx. This is really easy to evaluate now, because now the rho's will cancel, and you'll get the y bar is just the integral between a and b, a half of it, and then it will be f of x all squared dx, and then this integral is divided by the mass integral between a and b of f of x dx. Okay, these two, I can't stress enough, you need to have memorised. They're not in the formula booklet, you need to know them, and it's really easy. You just think about a general curve like that, you split it up into rectangles, and you treat each rectangle as having a centre of mass that's dead in the middle of the rectangle. So the x-coordinate is going to stay the same for an infinite slither of x, but the y-coordinate is just going to be half of all the y-coordinates, which is essentially half of f of x at all of those points. Yeah, that's pretty much it. So that's the case with lamina. With volumes of revolution, it's pretty much a similar thing. You have to do a very similar thing. So same deal. Let's start a new page. So for volumes of revolution, centres of masses, well, there's two cases, clearly. There's the case where you're rotating it around the x-axis. So say you've got a curve like this, let's say this y equals f of x, and it's being rotated about the x-axis, so it's forming some kind of funnel shape. So let's take the case where it's rotated about the x-axis. Well, in this case, y bar is clearly 0, and the centre of mass lies on the x-axis. Okay, so that's the first thing you can know. Clearly, the centre of mass lies on this central line here, the y equals 0 line, the x-axis. It's just a case of where on that line. And to work that out, it's fairly easy as well. What you need to do, it's the same deal. So x bar equals, now it needs to be divided by the total mass. And remember, the total mass is just pi times the integral between a and b, where let's say this up here is b, and that's been there, and a is back here. Integral between a and b of y squared dx. Okay, volumes of revolution stuff we've done before. I'm just trying to think at what point did we do it. Volumes revolution, we did it for calculus 8, I believe, so this shouldn't be a surprise. And then similarly up above, well, technically we have to times it by rho, right? But we will, again, for the same reason, for a uniform volume of revolution it's not necessary, because then for the bit above I need to do, for a similar reason, the mass times by the position. So it's just going to be pi times by the integral between a and b of y squared dx times by rho, but we also have to times by an x. And it's the same deal, x is the position of a particular slice, you know, that centre is going to be xi, and we're summing up all the centres of masses of all the circular discs as we're going along. Clearly I can take, I can take this constant rho out as a factor and put it there. You know, if you really wanted to, you know, you could cut all the middleman out and you could divide by pi rho top and bottom, and so it's just going to be integral of x times y squared dx between a and b over the integral of y squared dx over a and b, like so. You know, that's essentially it. Oops. So that, if I just tidy this up. Now in practice the pi and rho's cancel, we don't tend to write them, but it's always a good habit to get into. And this is for a rotation about the x-axis, and if I wanted the rotation about the y-axis now, then by symmetry all I need to do is swap over all of these things. So x bar in this case will be 0, because we've now got, you know, a volume being spun around the y-axis looking like this. So it's clearly on the y-axis. But now it's y bar we need to find, and for a similar reason it's just going to be the same as the top one, so it's pi times rho, but this time y is a and y is b, but this time it's x squared dy on the bottom, and we've got y x squared dy on the top between a and b, and this is pi rho. So it's exactly the same as the top, you just swap all the x's and y's over. It's just a fairly arbitrary substitution. It's not particularly difficult. So let me just tidy all this up. And a similar argument can be made not for solids of revolutions, but for what's it? Not solids of revolutions, but surface areas of revolutions. I'll leave that for you to figure out. It's honestly not that bad. You know, it's essentially it's using the formula for well, let's go through it then. So let's start a new page. So let's consider when we need to do the centres of mass for a hollow solid of revolution. So what does that mean? It means we're rotating. Let's say we're rotating around the x-axis this time. So let's say that's my shape. But now it's being rotated around the x-axis. So it's still forming the same shape, but now it's just creating a hollow cone, right? So there's only, it's a bell shape. The rest inside, this is empty. So the question is, where would the centre of mass of that be? Well, that's pretty straightforward. Y bar is still going to be 0. But x bar is going to be what? Well, let's remind ourselves what the integral is for a hollow. Well, what are you doing? You are taking a cylindrical disc, like so, and you're taking the just the line integral there. And the reason why you have to take the line integral of this bit is because what you want to do is this circle has radius y. So clearly the circumference of that circle, which is part of the revolution, is 2 pi y. But then you have to multiply by the length of that circle. And now you don't, the length of the cylinder. And now it's not just dx, it's actually proportional to this line segment here. And that line segment by Pythagoras is just going to be dy squared plus dx squared. And we will know that if we take dx squared out as a factor, dx squared, that will become a 1. I'll take dx out of the square root, and dy all squared becomes dy by dx all squared. And now this needs to be integrated between a and b. And now this is our mass function, just slotted in over here. Like so. For similar reasons, this is our mass, but we technically have to multiply it by some rho. That's just the area. Area times by density, it's going to be our mass. And then on the top, I need to do a similar thing. This time it's going to be by rho, by the integral between a and b of 2 pi y times by the square root of dy by dx all squared, and then plus 1 dx. And now remember that all these centres of masses are going to be the x coordinate, aren't they? Because all the circles will have a centre of mass in the middle, so I have to times it by the x coordinate x, and I'm summing them all up. I then notice that lots of things cancel, so x bar is just going to be 2 pi rho times by the integral between a and b of x times y times by the square root of dy over dx squared plus 1 dx, and this is all over 2 pi rho integral a and b of y times by the integral of dy by dx all squared plus 1 dx. Okay, so yeah, looks a bit nasty, but you can actually see the 2 pi rhos will always cancel, and then one integral is very similar to the other. The only difference is you're multiplying x into the top one, so maybe it will work out, maybe it won't. And then similar reason If I wanted to rotate around the y-axis, all that would happen is x bar is 0, and this would be the new formula for y bar, so you'd swap all the x's and y's around. And just for note's sake, say I had something like this, it was rotated around the y-axis, like so, and this was a hollow, and let's say this was x was some function of y, then this would be y, this would be x, and clearly x bar equals to 0 because the centre of mass would lie on the y-axis by symmetry, and it'd only really be y bar that we'd need to calculate, and this would clearly be 2 pi rho of the integral between a and b, where a is, say, one limit in terms of y and b is the other limit in terms of y, and it would be still, but rewritten, yx integral of dx by dy, all squared plus 1 dy, and this would all be over 2 pi rho integral between a and b of x integral dx by dy plus 1, and this thing's squared dy. So yeah, you're going to get very similar results. You just swap the x's and y around. It's honestly not that big of a deal. But yeah, unfortunately it's memorizing these integrals that are the problem. Now, the next thing I wanted to show you is there are what's called standard results of shapes that you need to be familiar with, of where their centres of masses are. And I think I'll go through one or two, but you're going to have to derive them yourself. And to be honest, it's actually good fun when you get it right. So I'm going to call these standard results. Okay, and these are given in the formula booklet. So don't panic about memorising these. You do need to know what they are though. This stuff here, if I was going to call it anything, I would put it a star because this is in further mechanics 2. It's good stuff though. When you get the hang of it, it's actually quite fun. But never mind. Okay, standard results. So I never remember this stuff, so I've got it written down somewhere. Okay, so let's talk about the laminas first. Okay, so if I've got a semicircle, well, you're given this, I'll tell you what, let's have a circle. Let's have a sector of a circle. This is supposed to be a circle with radius r, and this angle here is 2 alpha. Okay, that's really important. So for a sector, let's call this x bar, then the distance from O to x bar, i.e. from the centre, the distance from the centre of the sector of the circle to where the centre of mass is always going to be 2 lots of the radius times sine of a single alpha all over 3 alpha. Okay, so that's rule number 1. For a circular arc, let's say the O is here, and the arc is doing something like this, where from there to there is radius r, from here to here is radius r. Then x bar, let's say that point is here. Then for an arc, the distance from O to x bar is r sine alpha over alpha. And just to clarify, O to x just means the distance from there to there. O to x just means the difference from the centre from there to there. Please be aware that this angle in both cases is 2 alpha. Okay, if you're going to mess up, that's where you're going to be messing up, I guarantee. Now, there's various ways you could prove these things. You could do integrals. For example, I would probably consider a semicircular arc or a quarter circle arc like this maybe, and then I don't know, there's various ways you could do this. You could say you could let r equals to some constant, let's call it 1. So it's going to cut here at 1. Or you can just let r equal to r, and then, you know, what's going to happen here, let's suppose you start with theta as 0 and you go up to an angle here where that angle there is 2 alpha. I'll do this one for you just to show you how it would break down, but essentially you're going to have to do it yourself. What you would do is, clearly we've now got an r, this time we're going to have an r bar and a theta bar. Right, now clearly the theta bar, the angle of the centre of mass, is clearly going to be alpha, right? Because if I've got this sector, then clearly the centre of mass must lie on a line that's halfway off that sector. It's just a case of how much along that line it is. Now r bar, that's going to be fairly easy to work out, because we can just now use, well, we've seen polar coordinates now, so this isn't actually too much of a problem. So this is going to be, well, it's going to be over the mass function. Remember, that's rho times by the integral, which is going to be between 0 and 2 theta in this case, and it's going to be a half of r squared d theta. Right? That's fine. So that's the mass function. And now I've got to do the mass. I've got to do the mass of the thing up top. Okay, so what we're going to happen here is this is probably going to be some rho times by, and then let's think about this. How are we going to break this shape up? Well, it's going to be broken up into smaller sectors, isn't it? Well, let's say we've got a tiny sector like that. And what happens when d theta tends to 0? So it essentially becomes a flat line. Then r, the average point of there just becomes r over 2. Because if this whole thing is r, when this sector collapses down onto a flat line, the centre of mass is r over 2. So I believe this is going to be a half of the integral between 0 and 2 theta of r squared d theta, but you've also got to times by r over 2, so that's actually going to become a quarter, and r squared times r, that's going to become r cubed. Okay, you can times by 4 top and bottom, so then that disappears and this bottom one becomes a 2. You can divide by rho, so you've got this, and this will probably work out something nice as this up here. If you want to go through it, be my guest. You know, but all these good things you can just work your way through. That's probably how I do it. Just work through it. But I'm running out of time, because I really want to cut these videos down, and I'm 33 minutes and I want to keep it to an hour and a bit maybe. So now I want to look at solids, and you can do a very similar argument here with the solids. So the standard results that are given to you is that for a hemisphere, so let's say I've got my hemisphere, it's looking like that, and let's say the origin of the hemisphere is that bit there, and it's got a radius capital R, then x bar, the centre of mass of that, then O to x bar is going to be 3/8 of R. Okay, so it's just under halfway. So this is for, a solid hemisphere will look like that. Oh no, hemisphere's halfway, you silly boy. So this is a solid hemisphere. Okay, and now if I just rinse and repeat this, go over here, and now I don't want a solid hemisphere, I want a hollow hemisphere, also known as a hemispherical sphere. No, shell, not sphere. This is a shell. A hemispherical shell. Then, by similar construction, the length of O to X, which is this distance, i.e. from that centre to there, that is going to equal 1/2 of R. Okay, these are all given in the formula booklet. For a cone, like this, and this is for a solid right circular cone, then where that's the origin, that's R, and the height is from here to here, I'll call that H. Then X bar, this distance from here to here, so all these distances are, that is just 1/4 O to X, like so. It's also defined as 3/4 from the vertex, but from the circular base it's just 1/4 of H. And then if I was to have a conical shell, which is the same thing but just hollow, so a conical shell, then the only thing that would change would be, instead of a 1/4 H, it's now a 1/3 H. And you're probably thinking, oh, okay, how would I go about how would I go about integrating them? That's quite difficult. Well, what I would do, actually, the hemisphere and the hollow sphere would just be a volume of revolution of what you've done in the previous bits. That shouldn't be too difficult. And actually, so is the solid hemisphere and the solid cone and the hollow cone is. Because think about it, what you can do is you can create a line like this, where this is the radius and this is the height, and then you can rotate it 360 degrees about the origin, and you know the equation of this line is the change in height R over the change in base, which is hx, plus nothing. So you know y equals R over hx. So you can clearly tell that y bar equals to 0, and x bar is going to be rho times by the mass of this object. Well, if it's solid, it's going to be pi between what's this point here? That's h. So that's h and 0 of y squared, which is r squared over h squared x dx squared dx. And then the top, well, that's just going to be rho times by pi between 0 and h of the same thing, so r squared h squared x squared, but this time you've got to multiply by an x. That's actually going to be x cubed. And you'll see lots of things happen and cancel. You can take the r squared h squareds out as factors, and you'll see hopefully that things cancel down quite nicely. Yeah, where's my solids of revolution? I did it over here. Don't want a hollow solid. Yeah, it's the same formula as this thing up here. You just have to be really careful. Yeah, and it will all work out in the end. Coolsies. Well, got a bit of time. No, I've got a funny feeling this comes up in a question actually. Okay, right, so there's a lot to take on, I get it. I haven't gone through any examples, but that's what the last half of this is going to be about. So what I want you to do, if you're getting this so far, pause the video, give this a go yourself, read the question carefully, and we'll go through it. Okay, a uniform lamina is in the shape of a region R. Region R is bounded by the curve of the equation y equals 4 minus x squared, the positive x-axis and the positive y-axis, as shown shade in the figure. use algebraic integration to find the x-coordinate of the centre of mass. Well, that's just the first formula, isn't it? That's just going to be x bar is going to be rho times by the integral between, well, it's pretty obvious when y is 0, this thing here is going to be 2. So it's clearly from 0 to 2 of x times by the function of x, which is 4 minus x squared dx. And this is all going to be over rho times by the integral between 0 and 2 of 4 minus x squared dx, because this is just rho times by the area. It's a uniform lamina, so the rows are constant, so I could have taken them out. Technically I should have left them in, because they could have been functions of x's, but I took them out. So yeah, I think I just have to evaluate these integrals. Fine. So the bottom integral between 0 and 2 of 4 minus x squared dx is going to become 4x minus x cubed over 3 between 0 and 2. And since when I plug in 0 in there, that's going to be nothing, I've got 4 lots of 2, which is 8, minus 2 cubed, which is 8 over 3. So 8 minus a third of 8 is 2/3 of 8, which is 16 over 3. So I know at the very least, with this, the bottom is 16 over 3. Now for the top, I've got the integral between 0 and 2 of x times 4x squared, so that's just 4x minus x cubed dx. And so integrating that, it's just a power rule, 4x will become just 2x squared, then minus x cubed will become minus x to the 4 over 4, evaluated between 0 and 2. When I plug 2 in, I'm going to get 2 lots of 2 squared, which is 2 lots of 4, which is 8, minus 2 to the 4 is 16, but divided by 4 is going to be 4. So I think that's just going to give a 4. So x bar is just going to be 4 divided by 16 over 3, which cancels down nicely to 3/4. So use algebraic integration to find the x-coordinate of the centre of mass, not maths, it's just 3/4. So hopefully that wasn't too bad. I don't think I've made any mistakes. Nope, coolsies. Right, okay, a more difficult question. And sometimes with shapes, you have to remember what we were talking about with centres of masses and find the centre of mass of the whole object and then treat the thing that's missing as like a negative mass object, and it will just affect it in a similar way. So if you want to give this question a go, pause the video and we'll go through it. Okay, a uniform solid hemisphere of radius 6a and centre O has a solid hemisphere of radius 2a and the centre O. Remove to form bowl B as shown in figure 3. Show the centre of mass of B is 30 over 13a from O. Right. Okay, so first thing to note is that this has radial symmetry right through the middle of O popping out of the bottom. So that means the centre of mass is down here somewhere. You know, it's not pointing out a funny angle over there. So we really need to find this angle here. So there's two real shapes here. There's the positive mass, which is the hemisphere, like this, which has radius 6a. So that means its mass is going to be pi times r squared. So that's 36 pi a squared times by some rho. And we've actually got a negative mass object, which is the smaller bit, which has the same origin O, and its radius is 2a, so its negative mass is going to be pi times that squared rho, so that's 4 pi a squared rho. Next up, if I consider where their centres of masses are, so the centre of mass of the first one, centre of mass, of the first one. I look back to the standard results to see the hemispherical shell. The solid hemisphere, which is over here, is 3/8 of r. So for the first one, it's going to be 3/8 of 6a, and for the second one, it's going to be 3/8 of 2a away. So now I just have to remember and go back to the previous thing. So if I say O to x bar, this is just going to be the individual centres of masses times by their masses, so the two green things times together, divided by the sum of masses. So it's going to be all over 3/8 of 6. It's 18 over 8, isn't it? And that cancels down nicely to 9/4. So it's going to be 9/4 of a times by its mass, which is 36 pi a squared rho, minus, because it's a negative mass, and now 2 times 3/8 is 3/4. This is going to be 3/4 of a times by its mass, which is 4 pi a squared rho. And this is going to be all over the total mass of the object, which is 36 pi a squared rho, minus 4 pi a squared rho, which I believe is 32 pi a squared rho. So lots of things are going to happen here. For a start, we can divide by rho, so all the rhos cancel. We can divide by a squared, so all the a squareds cancel. We can divide by pi, so all the pi's cancel. So actually this whole thing is just going to be in terms of a, which is what we'd expect. So let's tidy this up. So O x bar is going to be 9/4 a times 36. Well, 9/4 of 36 is, wow, 81. So this is going to be 81a minus, and then 3/4 of 4. Well, that's just 3a, and this is all going to be over 32. So what is 81 minus 3, which is 78, and 78 over 32, that is 39 over 16a. Is that what we wanted? No, I've got 30 over 13. Where have I made a mistake? Solid hemisphere is 3/8. Yeah, that's weird. A uniform solid hemisphere of radius 6a. Okay, so its mass. Oh my god, that is where I've gone wrong. Oh, it's a hemisphere. These masses are completely wrong. I'm such a silly. That's if I was treating it as a circle. It's not a circle. I'm such a wally. This is just complete wrong. Okay, so what is the volume of a sphere? The volume of a sphere is 4 pi thirds r cubed. So the volume of a hemisphere is just 2/3 pi r cubed. So what is 6 to the power 3? And then times that by 2/3. So this should have been 144 pi a cubed. And then I need to do 2 to the power 3 and then times that by 2/3. And that would have given 16/3 pi a cubed. Right. Okay, sorry. I treated them as circles. They're clearly hemispheres. They're volumes. So what have we got? Maybe I should have tidied this up. So 3/8 of 6 is 18 over 8, which is 9/4 of a. And then 2 times, that's 3/4 of a. So I've actually got 9/4 of a times by 144 pi a cubed minus 3/4 of a times by 16/3 of pi a cubed. And these are times by rho, but whatever. It's just going to cancel out at the end. And this is all going to be over 144 minus 16/3, which is 416 over 3 pi a cubed. So the pi a cubes are going to cancel top and bottom. So I've got 9/4 of 144 which is 324, minus 3/4 of 16 thirds, which is 4, and this is all over 416 over 3, and this is A, lots of that. So 324 minus 4, and this is 320 all over 416 over 3. Whew, and that turns out to be 30 over 13A, which is indeed exactly what I wanted. So yeah, man, I used circles instead of volumes. That's pretty lame. Okay, but yeah, it worked out in the end. Okay, so my bad. Okay, what have we got here? The bowl B is fixed to a plane face of a uniform solid cylinder made from the same material B. The cylinder has a radius 2A and a height of 6A, and the combined solid S has an axis of symmetry which passes through O. Show the centre of mass of S is that from O. Okay, well, first of all, if this is a solid cylinder made from the same material, that means their densities are the same, so we can just plug them straight in. So this centre of mass here is clearly going to be 3A from the bottom, or 3A from the bottom there, like so. So from O, let's think about it. From O's perspective, if Y is going downwards, then the mass of the bowl itself is going to be 416 over 3 pi A cubed. So this is the mass. And the centre of mass, well, we just said from O was what? 30 over 13A. Now, this was the bowl. Now, if I want to take the cylinder, what is its mass? Well, it's just pi r squared times by h, isn't it? So it'll be 2 squared, which is 4, so that'll be 24 pi A cubed. And its centre of mass from O is 6A plus another 3A, which is 9A downwards. So I'm guessing all we need to do is 416 over 3 pi A cubed, times that by 30 over 13A, plus 24 pi A cubed times by 9A over the joint mass, this is Y, of 416 over 3 pi A cubed plus 24 pi A cubed. Everything has a factor of pi A cubed involved, so I can divide by pi A cubed top and bottom. So it's all in terms of A, that's nice. So on the top, I've got 416 over 3 times by 30 over 13. Okay, so that's 320A on the top, plus 24 times 9, which is 216, and then this is all over 416 over 3 plus 24, which is 488 over 3, and this is an A. So if I take the A's out as a factor, then what is 320 plus 216? And I want to divide that by 488 over 3. And that will give me 201 over 61A, which is exactly what we wanted. Okay, the plane surface of the cylindrical base of S. Okay, so the combined solid is S. So the plane surface of the cylindrical base of S is placed on a rough horizontal plane inclined at 12 degrees to the horizontal. The plane is sufficiently rough to prevent slipping. Determine whether or not S will topple. Okay, maybe I haven't talked about this. Well, here's a good time. So here you go. Here's my plane, and this is 12 degrees. Well, let's say I don't draw this shape accurately. Let's just say it's just represented by a box. That is terrible. It's represented by a box like that. The centre of mass is acting somewhere there, and I know what this height is, or rather, well, I know what that height is now actually from the bottom. It's quite easy. because if it's 201 over 61A from O, well, what's this total height here? This total height here is 12A, isn't it? Because I've got 6A of there and 6A there. So really all I need to do is 12 minus that fraction, which is 201 over 61, and I get 531 over 61A. Okay, now here's the deal. For an object to topple, the mass is always acting downwards. Okay, now when the centre of mass is acting, and this line, this purple line, okay, it's always acting downwards. But if it was acting in such a way that, see how the purple line is just touching that corner of the solid, then it's fine. As soon as that mass is acting downwards in such a way that it's past that point, we're in trouble. So, if it's on the point of toppling, so determine whether S will topple or not, what we need to do is think very carefully, is this the case or not? So, what do we need to do? Well, what's this length here? This length is just the width of that, which is 2A, and this height here is 53 over 61A. So if I want to work out this angle theta, say, then clearly tan of that theta is the opposite, which is 2 over the adjacent, which is 531 over 61. And if I inverse tan that, so 2 over 531 over 61, I will get that theta is, in terms of degrees, so shift tan fraction 2 over 531 over 61, I will get theta is 12.93 degrees. Now here's the deal. For this to topple, it needs to be, this angle, theta, that theta value needs to be greater than 12.93 degrees to topple. Right? When theta is 12.93 degrees, this thing will topple, because as this thing opens out and says go over there, then the mass is clearly toppling. Well, let's try and figure out if there's any similar angles here. Well, for this to topple, and say this was to be going straight down, so this is 90, then if you think about it, by similar triangles, this angle is the same as this one. This is a 90 and this is a 90, so this must also be theta as well. And since we know what theta is, and it's exactly 12 degrees, in actual fact, it will not topple, as it's 0.93 degrees too shallow to force a topple. So this shape will just hold on. It will just hold on. As long as friction is, you know, rough enough to not let the shape tip over. If this was 13 degrees, then this angle would be too steep, and what would happen is the whole thing would roll over, it would topple. But 12 degrees is fine. Okay, so maybe I skimmed over that a little bit, but there you go. I'm just trying to think if I've skipped over anything else. No, toppling points and using... actually, no, having said that, I think I did talk about toppling in my previous video, didn't I? Centres of masses, if you had like a laminar on something. Yeah, I'm pretty sure I did. Anyway, no, it's the same deal for this, exactly the same. So if the mass from the centre of mass is acting in such a way that it kind of, you know, it acts over something, and this angle is sufficiently large enough, then the whole thing will topple. Okay. Right. If you want to give this a go, pause the video, see how it goes. Okay, a thin, uniform, right hollow cylinder of radius A and height 4A has a base but no top. A thin, uniform hemispherical shell, also of radius A, is made of the same material as the cylinder. The hemispherical shell is attached to the open end of the cylinder, forming a container. It's a bit like a thermos flask. The open circular rim of the cylinder coincides with the rim of the hemispherical shell, so yeah, it fits nicely. The centre of the base of C is O, as shown in the diagram. Find the distance from O to the centre of mass C. Well, you've clearly got some radial symmetry going on here, i.e. if I was to draw a line straight up from O, like that, through the tip of this, then the centre of mass probably lies somewhere on here. The trick to this is there isn't actually a formula for a hollow cylinder, but what this is actually really sneaky. What you've got to do is you've got to split this up into 3 parts. Okay, there's the circular lamina on the bottom. There's the curved surface area of the edge, if you like, and then there's also the hemispherical shell. Okay, yeah, that's pretty much it. So, well, the circular lamina, that's quite easy. Its mass is just going to be pi a squared times by rho, but you know, I think it's all made of the same material and it's uniform, so you don't have to worry about like rho being a factor or anything. And then the centre of mass, and the centre of mass of this, if we treat distance from O, well, that's just 0. It's just at O, so that's not a problem. We've done that one. Next up, the curved surface area edge. Well, the centre of mass of it, that's quite easy. That's just going to be 2a from O, so that's not a problem. And the mass, well, that's just going to be proportional to the surface area. So what's the surface area? It's going to be the circumference of the circle, which is 2 pi a, and then it's times by the height, which is 4a, so I actually make that 8 pi a squared. So already we're plodding along, you know, we've got the mass and the centre of mass for the curved bit, and now the hemispherical shell. Well, the mass is quite easy because the surface area of a sphere is 4 pi r squared, isn't it? No. Oh dear. Yeah, I think it is 4 pi r squared. Pretty sure it is. Let me just double check that. My brain's all over the place. Surface area of a sphere is most definitely 4 pi r squared. So the surface area of a hemisphere would just be 2 pi r squared. So since r is a, then this is just going to be 2 times pi a squared. And the centre of mass of this thing, well, we know for a hemispherical shell, it's 1/2 from the centre, i.e. from here. So it's 1/2 of a plus the 4a, which is actually 9/2 of a from O, remember. You've got to remember it's all got to be from O. And now actually we're ready to go, right? Because now to work out, well, if this is x bar, then to work out O to x bar, that's really easy. That's just going to be the mass of the circular bit, pi a squared times by the distance away, O, plus the mass, the curved surface area, which is 8 pi a squared times by its distance away, which is 2a, plus the final mass, which is 2 pi a squared, the hemisphere bit, times by its centre of mass away, which is 9 over 2a. And this is all divided by its total mass, which I believe is 11 pi a squared. Because I've got 1 pi a squared plus 8 pi a squared plus 2 pi a squared, which is 11 pi a squared. So same deal, the pi a squareds can cancel everywhere. This is 1 times by 0, so that can disappear. I've got 11 on the bottom. I've got 8 times 2a, which is 16a, plus 2 times 9/2 of a, which is 9 of a. So I've actually got, it looks like 25 over 11a. Okay. 25 over 11a is just over 2a. So the halfway point of the cylinder is 2a, so it's some nudge above halfway. And that kind of makes sense because the hemisphere you would expect to contribute more to the weighted average, so it'll be pulling the centre of mass upwards a little bit. So 25 over 11a seems realistic. Okay, the container is placed with its circular base on a plane which is inclined to theta degrees to the horizontal. The plane is sufficiently rough to prevent C from sliding. The container is on the point of toppling. Find theta. Okay, so I've got my plane, my inclined plane like so, and I've got my object here looking a bit like this, like that. And the centre of mass somewhere here needs to be pointing straight down, and it needs to be touching that corner such that this angle theta is there, and by similar triangles that should be the same as this angle theta here. So do I know for this special right angled triangle here what's going on? Well, the base of it is just A, and the height of it I've now worked out from O, which is 25 over 11a. So now I just need to do the inverse tan of the opposite, which is A, over the adjacent, which is 25 over 11a. The a's cancel, so this is just the same as the inverse tan of 11 over 25, is it not? 1 over 25 over 11 just flips it. So inverse tan of 11 over 25. So you're looking at a theta value of 23.749 degrees, but I'll treat this as 24 degrees to two significant figures. So if theta is bigger than 24 degrees, this thing is toppling over and it's going to roll down the hill. It's going to topple. Coolsies. Yeah, it wasn't too bad. Okay, last one. Pause the video. Give it a go. Right, a uniform solid right circular cone has base radius A and a semi-vertical angle of alpha. Interesting. Where tan of alpha is 1/3. The cone is freely suspended by a string attached to a point A on the rim of its base and hangs in equilibrium with its axis of symmetry, making an angle theta with the upward verticals shown in figure 1. Find to one decimal place the angle of theta. Ooh, this is interesting, because what's happening is if this thing is in equilibrium, that means the centre of mass is acting straight downwards like this, so the centre of mass is here. So it looks like by corresponding angles that this angle is theta here. So if I can work out the centre of mass of this cone and the distance of where it is from there to there, then I can work out what theta is fairly quickly. So maybe it'd be an idea to just draw this cone out again and label a few things. Well, this radius is A, but what's the height? That's interesting. Well, I know that if I was to split this cone in half, this angle here is alpha, where tan of alpha equals to 1/3. That's interesting, because that means tan of alpha is the opposite over the adjacent, which means for every one of the opposite there's 3 of the adjacent, which means that if this is A, then H must equal 3A. Okay, do you get that? Because for this to work, it must be A over 3A, so that cancels, and that's 1/3. Now, this is a solid right circular cone. So I can work out what the centre of mass is from a right circular cone because it's one of the given results that's given in the formula booklet. And a solid right circular cone is 1/4 of the height from the circular base. Now I know what h is. H is 3a. So actually the distance from here to where that is 1/4 of 3a, which is 3/4 of a. Okay, that's actually not too bad. So now I've got that this distance from here to here is 3/4 of a, and this distance from here to here is a. So that means tan of theta is the opposite, which is a, over the adjacent, which is 3/4 of a. The a's cancel. 1/3/4 means that tan of theta is actually 4/3. So all I have to do now is inverse tan of 4/3, and I get that theta is 53.1 degrees. Coolsies. Yeah, that's it. Pretty straightforward. Just thinking, have I made a mistake there? No, the solid right circular cone is 1/4 from the circular base. It's hanging in equilibrium, so the centre of mass is directly hanging below it. No. Cool. Alright then, guys and girls, hope you enjoyed that. And yeah, have fun.